Okay, question 7. This looks like a year 1 exponential modelling type of question. If y equals a times b to the power of t, then for part A we need to take log to the base 10 of both sides. Make sure you show you're working out for this, since the answer is given in the question. Using the rule of logarithms, we can split this up into this, and then you can bring the t down to the front here, which gives log a to the base 10 plus t log b to the base 10. And that's pretty much it. We should probably just rearrange the right hand side so it looks exactly as it looks in the question. Okay, so in this question, that is going to be C. In part B, we've got a graph that's been drawn which is log y against t. So it's log y against t, which is effectively this is y, this is x, because the graph is this against this. Now that would make, if you it's a straight line graph, as it says in the question here. So since it's a straight line graph, that would make this the gradient m, and this would be the y-intercept c. So the gradient in this question, is going to equal log b to the base 10, and the y-intercept is going to equal log a to the base 10, and tells us in the question the gradient is this minus 0.076, so that will equal log b to the base 10, and the y-intercept is 2.23, so that means 2.23 equals log a to the base 10. So we need to get rid of, we need to get b on its own, and we need to get a on its own. So if to get rid of log to the base 10, we can just raise both sides. We could just do 10 to the power of both sides. So if we do 10 to the power of the left hand side and 10 to the power of the right hand side, this will cancel with this, and we'll be left with b on its own. So if you type 10 to the power of minus 0.076 into your calculator, you should get 0.84 to two significant figures. I think it's actually 0.8394 something, but it's 0.84 to two significant figures. In a similar way, if you do 10 to the power of 2.23, you will find out that a is 169.8 something, which works out as 170 to two significant figures. So those are the two answers. B is 0.84 and A is 170. So in part C, it's a good idea to write out what we know now. We know that A is 170 and we know B is 0.84. So if you look at this, this is like a geometric series now. So at the initial time, there are 170 milligrams in the patient's bloodstream, and then after 1 hour you would times this by 0.84, and that would tell you how much is in the patient's bloodstream after 1 hour. So this is after 0 hours, 1 hour, 2 hour, 3 hours, and so on. So each hour you're multiplying by an extra 0.84. So in terms of interpreting these two values, A and B, we can say that A is the initial value, which is the amount of milligrams of antibiotic initially given to the patient. So we can say 170 milligrams of antibiotic were initially given to the patient. Now, in terms of what does the B represent, what does that 0.84 represent? Well, as I said before, it's similar to a geometric progression. B is the common ratio, what you're multiplying by each time, and since you're multiplying by 0.84 each hour, that is in effect reducing the amount of antibiotic by 16% each hour. So I think that's the best way of saying it. We can say that the amount of antibiotic reduces by 16% per hour. We should probably say approximately there, because it wasn't exactly 0.84. Okay, so we know that y equals 170 times by 0.84 to the power of t, and in part D it says find the time for the amount of antibiotic to fall to 30 milligrams. So if we put y equals 30 and try to solve this equation, we need to work out what t is. We need to divide, before we take logarithms to find t, we need to divide by the 170 first. A lot of times when I'm marking questions like this, students forget to get rid of this before they take logarithms. So if you divide by 170 first, you get this. Then you can take logs of both sides. It doesn't matter what the base is. So if we use natural logarithms, log to the base e of both sides, we'll have this equals this. And the reason logarithms are useful is because now we can bring that t down there, and that will give us t ln 0.84 on the right hand side, and so the left hand side will stay as it is. And so if we want to find t, all we need to do is divide the left hand side by ln 0.84. So t is all of this divided by ln 0.84. It's always a good idea to use the exact value of b that you got rather than 0.84. And if you type that into your calculator, you should get 9.94876 something, but it says to round to one decimal place. So, well, I'll just write down 9.9487 and so on. So therefore the time is 9.9 hours to 1 decimal place. Okay, in E you've got to comment on the reliability of your estimate in part D. The key to part E, the reliability, is to realize that in this experiment all the data was taken from 0 to 5 hours, the first 5 hours, whereas the prediction you've just found is 9.9 hours, which is way beyond the experimental time period. So I think the best way to answer this is to say it's going to be unreliable. I would say something like as the time is 9.9 hours, and the experimental data was between 0 and 5 hours. That's way beyond the experimental data period, so it's extrapolation. So I would say it's fairly unreliable, this prediction. So I would say therefore extrapolation beyond experimental time period. Let's just clear a bit of space over here. Experimental time period. So that implies unreliable estimate. I mean, it could be okay, but looking at the mark scheme here, it says the estimate should be treated with caution.